And I share my screen. So I will start today's lecture by reviewing two subjects, quantum parallelism and Simon's algorithm. So I want to remark that the Simon's algorithm is a more advanced topic. So in the slide, I sort of mark as a star. So if you do not understand the detail, it's okay. You can skip this in your first reading, and you can always come back later. Okay, but I'm going to review that. But I want to reassure you that in order to understand any of the algorithm, you should keep in mind the three principles that we discussed. So first, we can use superposition, right, and then send into the black box, which I don't want to draw here, right? So there is a black box that implementing u of f, which you compute the f of x here and then add it to the second register. So then you get a massive question answer entanglement. And this is really just due to the linear property, the superposition principle, and the gate is linear and unitary, right? So this is really just using the first two principles and you have this. So this is really a direct consequence of really basic rule of quantum mechanics, right? And then the third rule comes in, but it has some negative effect because in order to read out, you need to measure, but when you measure, let's say, when we measure and I get, let's say, 1 here, this means that I project my answer, the second register, to f of 1. But sometimes we will get the first register to be 0, and sometimes 2, etc. So it's random, and that seems to be a problem, right? But I remarked that you could be smart and then design some measurement. So for example, you could measure the second register. These are f of 0, f of 1, f of 2. And then you could get, for example, measure the second register. So for example, measure second. And then you get the value to be f of f sub 0. So then first register collapse to a subset, but still a superposition of x such that f of x is f of 0. Okay, so at least measuring in this way, it gives us more, it gives us those x which evaluate f of 0. So it gives us some property, maybe symmetric property, periodic property of the function. Okay, and while you are reading the Simon's algorithm, maybe you should focus on where these rules apply. Okay, so let me just illustrate. This is the problem we want to solve. There is a hidden string. There's a hidden string S such that the functional evaluation become equal if and only if the two arguments differ by this string S, or trivially when they are the same. Okay, so the goal is to find this S. And here is the summary of the algorithm. Okay, so just ignore one. You prepare this, right? Prepare this. This is exactly what we do here. You prepare all possible input, and then you have a blank register that you could store the answer. And after the circuit of the F, then you get these massive question answer superposition. And the step 4 here says measure the second register. This is what I say here, right? So if you measure this collapse to superposition of X such that f of X equal to F0, right? So if you measure the second register, this would collapse to, okay, let's say second register give me F0, but this means that first register is now in a superposition of those X that evaluate to F sub 0. But according to what's promised here, right? That what's promised here, there's only 2, right? There are only 2. There could be some X0 and then X0 plus S that evaluate to F sub 0, right? So this is the first register, right? So now we can take advantage of that because from the previous discussion, if you do a Hadamard gate, this will be, part of it would be your homework. You've applied a Hadamard gate, to this, right? And remember that it's in the superposition of Z that is orthogonal to S. So you would get this. So this is proportional to that. You can go back to the previous slide and see the exact expression, but this means that the Z, after you perform the Hadamard gate and then measure the first register, now you measure the first, right? So when you measure, you will get Z that's orthogonal to S, right? And okay, this is denoted by W here, but you do it many times. You repeat the same procedure many times. You get a set of W, which is orthogonal to S. So then it reduces to a classical problem that you solve this equation. Okay. Question? I seem to see some. Yes?
Seems like someone's audio is not syncing with your the video.
Okay, but can you hear me?
Yeah, we can hear you. Some of us can hear you fine, but one.
Okay, that probably is due to internet. Okay. Yeah, it might be due to the internet. But I don't think I can do anything. Maybe I just try to pause as much as possible.
Yeah, probably he should close and re-enter. But
it's also, yeah, that might also be a solution. If you exit and come back, maybe it will sync. Okay, but if most people have the problem, then maybe have to restart this. But for the moment, that probably doesn't seem to be an issue for the majority. Okay. So I just want you to focus on where the three rules apply, right? So there's a superposition of the questions, and using that linearity, you get a superposition of questions and answer. And now you have to be smart in measure. Here, we measure the second register first. This is useful in terms of thinking, but in fact, you can actually skip this because the later Hartmann gate and measuring the first register would automatically pick up some WI. But this is also useful in terms of explaining how it works. So, but if you don't remember, if you don't understand this comment, this is fine. Yes?
In step 6, does that mean we measure WI many times until we get dimension n-1?
So we measure, so you do it once, you will get a Z or WI, right? Each time you run the procedure, you get a WI. You run it again, you get another W, and until you collect enough that you can constrain the S, right? If the dimension is n, if you get n-1 independent vector, then you can infer that the remaining vector, right? Yeah, but this is the classical part, right? But if you focus on the quantum part and where the rule applied, I think you have a better way of understanding this. In fact, this is almost the universal rule in designing quantum algorithm, right? I have seen previously Deutsch algorithm, Deutsch-Jozsa, Vasarani, Bernstein algorithm, they share this. Okay. Yeah, so last time I started the material of the second week. So I'm going to start it again. So, but the point is that in quantum entangled state have correlation stronger than classical states, as you will see from the so-called Bell inequality. And then you will also see that these states are also useful in terms of doing some tasks. So for example, in teleportation. Okay, but this is the subject of today's lesson. And last time we talked about there's a simple equality that if you have 4 random variable, which can only be plus or minus 1, then this equality holds. This combination of the 4 variable give you only +2 or -2, right? And if you have many of these, and then you do average, you still fall within this range, right? -2 and 2. And E basically represents some averaging. So averaging comes from some probability distribution. This is from distribution. So it doesn't matter what kind of distribution, you would evaluate this combination and you will fall into this range, -2 to 2. Right, so for a particular EA, it's basically taking a measure. As we'll see, you can imagine there's an A here and B here, and this place is performing some measurement. It will get +1 or -1, +1 or -1, and has different choice of observable, A prime, B, and B prime. For a classical object, you always get such combination in this value. Okay, and this is easy to remember that you use A prime, B prime. This is plus, and this is minus. Okay, so this is where that is. Okay. So this is basically here is rewriting of what was in the last page. Right? So it's really a rewriting of this row. I'm trying to use the same symbol. So this is basically just recap what you have from last slide. Suppose that this distribution come from some kind of variable we cannot know, we cannot detect, but there's some variable, maybe that variable here, row, and give rise to a distribution. That this variable give rise to a distribution. And capital A and capital B denote the observable or the measurement value you will get. So these will be plus minus 1. It's random, but somehow this expectation value, this correlation, if you want, if you have two different choices of axes, A or A prime, B or B prime, the previous inequality give rise to this combination being less than 2. Okay, so let me just go slowly here. So let me just read this. So capital A, capital B are the value that you measure would only be plus 1 or minus 1. And in terms of this local hidden variable is that somehow the value that you would measure, you will get, is already determined when the particle leave the source. And it's just randomly distributed. Okay. So it's called a local hidden variable or local realistic theory, because whatever you will measure is already determined right here. It's just you don't know what it is, and so you prescribe some distribution, but it's unknown. Okay, and there's also a constraint that whatever the outcome on the A side, it should not depend on the setting, the measurement setting on the B side, whether it's B or B prime. That should not affect what you would measure the statistic on this side. And it's obvious here because this is a separate value, right? So whatever A measure does not depend on B. And here describe their joint measurement. Okay, but in quantum mechanics, you can actually violate this inequality, right? So now I have to explain what this is. In quantum mechanics, you measure the observable. So on the A side, you're taking a measurement apparatus, like measuring the spin. Maybe you're using A or A prime, and using B or B prime, some measurement axes. So in terms of quantum mechanics, this is also some kind of correlation, but in order to determine what that value is you need to evaluate respect to a quantum state, right? And this you need to repeat measurement process many times. This expectation value means that if you do it many times, that's the average value you will get. So that is, you record whether it's plus 1 here, minus 1 here. This is basically what this observable will give you, and that observable will give you on the B side. You record with plus 1 on the left or minus 1 on the right, and you multiply them together. You repeat it many times. From an experimentalist point of view, it's the same whether it's classical or quantum. But in terms of calculation, there is a difference. Here you would use the quantum mechanics to evaluate this expectation value. Okay. So here I just introduced like a symbol to representing the combination, right? This is, remember, it's like A, B for the classical. It's the corresponding thing. The classical is this AB plus A B prime plus A prime B minus A prime B prime. Okay, but in quantum mechanics, it's convenient to define observable here. What this means is that classical, I have that combination to be less than 2, but for quantum mechanics, if you choose a specific state, this is an entangled state, it's a singlet state, and if you optimize the axis, the orientation of the combination of these axes, you will find a setting which give the value 2 square root 2, which is sort of it's roughly a 2.82, and which is greater than 2, and it's substantially greater than 2. Okay, in your homework you would perform the calculations, but the upshot is that the measurement setting for the A is the angle pi over 2, 0. The two different setting on the B side is pi over 2 and 3 pi, sorry, pi over 4 and 3 pi over 4. And it's easy to just show what it looks like here. So this is the measurement setting on the A side. So you have two settings. I'm denoting this as x-axis. These z-axis are measuring the angle like this. So the first choice is pi over 2. The second choice is 0. And for the B, the first choice is pi over 4. The second is 3 pi over 4. Okay. And yeah, so this 2 square root 2 is the maximum you can get from quantum mechanics. And it's greater than 2. So that means if I can perform an experiment and verify that I'm getting close to 2.8, then I can rule out the classical theory. And quantum mechanics would be perhaps the correct one. But you cannot rule out that it's maybe there'll be other theory that could also give you 2 square root 2. So you cannot rule out quantum mechanics, at least it's consistent. Okay, so for any quantum state, to derive the maximum violation, it's a math problem, and people already have figured that out. So let me pause here to see if you have any question. Maybe from chat. Y95, it's a difficult math problem. Yeah. Some problem, they're easy to state, but difficult to prove. Okay. Yeah, so that will be the exercise. And in fact, I already posted homework too. So you will be proving this equality, and then you will also show that under the maximum setting of the measurement axis, you get 2 square root 2. Okay. Then I want to talk about a related equality and how the inequality related to a game. I should say it's the inequality and the related game, imaginative game between two players and a referee. So let me describe this game setting. So there is a referee who give a variable, just one bit variable x and y, x to Alice, y to Bob. And Alice and Bob need to each produce a bit. So Alice produced a bit A, Bob produced a bit B. And this is a game, and to win the game, they need to produce the 2 bits, A and B, such that A adding B, the binary addition, should equal to the X and Y, the end of the 2 variables X and Y. So that's the game. Okay. So Alice and Bob need to have some strategy, right? So, and that strategy may be described by a probability distribution. Some strategy, if I get X to be some value, Y to be some value, I would produce A and B in some probability distribution. Okay. This, in the context of this, is usually called a box. So the question that we like to ask is, how do we win this game? What is the maximum probability of winning the game? Okay. And it turns out it depends on the model. Like what kind of model would determine how much you can win the game. So for example, if this probability distribution comes from classical theory, so the limitation is that Alice and Bob cannot have any communication. They can design their strategy in advance. They can share some in the quantum mechanics. They can share maybe an entangled state, but they cannot have a direct communication. Okay, so how to win the game depends on whether it's a classical theory, whether it's quantum theory, or it's beyond quantum theory. Okay, and it turns out, so we won't be able to show how this is derived in rigorous way, but if A and B are classical player and there's no way to communicate, there's no signaling, then the maximum probability of winning is really 75%, so 3/4. Okay, this you could probably understand this way, but I cannot prove this maximum here rigorously. But let's see X and Y, right? And if there are only 4 possibilities, X and Y, so if it's 0, 1, 0 and 0, you would get 0. So this is 1, 0 and 1 is still 0, 1 and 0 is still 0, 1 and 1 is 1. So looking at this, you have 3, 0 and only 1, 1. So I could design a strategy that I always output 0, A equal to 0, B equal to 0, right? That looks like a stupid strategy, but in terms of this, I'm going to win 3/4 of the time, right? And it turns out that this is the best strategy that you can have. And it failed when X equal to 1, Y equal to 1, the end give you 1, but A and B is 0. So this is the case where you fail. Okay. And for quantum mechanics, it turns out the winning probability is achieved by using an entangled state. So it will be something like up, down, minus down, up state that we just mentioned earlier in the Bell inequality. And the way to do that is the X equal to 0. Y is the choice of A prime A or A prime. Right. Y equal to 0, 1 is a choice of B and B prime axes. And then you just measure the observable, just like the previous Bell inequality. You, for example, if x equal to 0, then you choose this. If x equal to 1, you choose this. And if y equal to 0, you choose this. And y equal to 1, you choose that. And you perform the measurement. And if you get +1, so if you get +1, you output bit 0. If it's -1, you output bit 1. Okay. It turns out that you cannot win it 100%. You only win it about 85%. This square root 2 is related to the 2 square root 2 in Bell inequality. Okay. And you could also ask the question, is a way to win it 100%? And we know that's not possible for quantum mechanics. But two guys, Popescu and Rohrlich, they propose a box, meaning they propose a distribution or strategy to win this. So note that they cannot communicate, right? And even for quantum mechanics, there's no communication between Alice and Bob. They only infer what they should do by the measurement. In order to make sure that this is the case, the box need to obey the so-called no signaling probability, meaning that if I'm given x equal to 0, y equal to 0, for example, doesn't matter Bob's value. If I just sum over the Bob's possible value, it should be the same if Bob is given a different bit. So I should say, maybe I should highlight the difference here. Meaning that the probability distribution should not change even if Bob given a different instruction, because Alice has no way to know what Bob would do. So this is the so-called no signaling condition. There are many ways to give such a condition, but this is one of the way they choose. So you need to satisfy this. But you can see here, so you can check whether this would give rise to the winning. So if, let's say, if x is 0, y is 0, so 0, 0, 0, 0, right? So the probability, there are only two possibilities. Alice output 0, Bob output 0, or Bob and Alice also output 1. So this means that the addition, the binary addition, give me 0. Binary addition give me 0. It's the same as multiplication. So I win it 100% if x and y are 0 and 0. And you can also verify if this case x and y is 0 and 1, and they also add up to 0 because the n is 0. So this is the first three groups of the n0 case, right? The non-trivial case is here, and you see that it's almost the same, but they flip this. So P01/11, P1011. So the first three groups have the symmetric output, and the last would have sort of anti-symmetric. So you can check that this is also allow you to win. Okay, so you can check this wins 100%. So in fact, you can also use this box to violate the Bell inequality, the version that we presented, and give the value B equal to 4. So this means that the so-called PR box has a correlation stronger, even stronger than quantum mechanics. So in terms of correlation, quantum mechanics greater than classical, but the PR box has correlation also greater than that. But this is already beyond quantum mechanics. Yeah, and this is also a full form of research area. People discuss beyond quantum mechanics. But as far as we know, quantum mechanics is up to now still the correct theory. Nobody can find a violation of quantum mechanics at this point. Okay. Any question?
I have a question. So I'm still a bit confused about no signaling. Why is it a sum of probability instead of just individual probabilities?
Individual probability would be too detailed to constrain. So because you should say that it doesn't matter what the B is, right? The axis is then the required to be summing it to be the same. I mean, it's one of the choice. You could also develop a condition that you require individual to be the same, but this would be too constrained.
Okay, so if this equality is satisfied, does that imply they're not communicating with each other?
They're not communicating. Yeah.
Okay, I don't.
This is maybe it's you could. It's probably we don't have time to talk about the detail here. I can point you to the reference. You can go check with the reference.
Okay, thanks.
So maybe I should put a star here. If you don't, I'm just want to point out there's even you can think about things beyond quantum mechanics. It's really a nice way of extending your imagination. Okay. I should do a poll. Let's see. This is related to the subject that we just did. Maybe take 1 minute. And I think, yeah. I think in the recording, the poll will not show up. So maybe at the end, when I share the results, then I can see if I can share the screen of that, and so that it can be recorded into the video. Let's take 10 more seconds. Okay. Let me see if I can share this. It does not show up. Yeah, unfortunately, I cannot share this. Let's see if there's any way I could. What I would do, this is just so that we have the poll that would show up in the recording, because I checked the recording that it does not do that. So let me stop sharing. Did you see the share results or not yet?
No.
Okay,
Yeah.
so this is the share result. Thing is that I cannot make this go into the video. Okay, so I will just let you read this, and I can really just copy and paste that. Okay. Okay. So the correct answer are all of them. So classical theory can achieve value of 2. Let me just yeah, quantum mechanics violate and achieve a value of 2 square root 2. This is the maximum. Okay, and this BFX can violate the inequality and achieve a value of 4, which is the absolute maximum you can get. Okay. Let's see. I stop sharing, but let me share my screen. Okay. Can you see my slides? So yeah, so while you are reading the result, I try to copy that as image. Yeah. So at least this will go into the recording. Okay. So yeah, just to give you a bit more on quantum mechanics, how strange that is. There is something that does not require probability distribution. So I just show everything here. So if we consider 3-party state, so this is so-called GSZ state, Greenberger-Horne-Zeilinger state, in this particular form, and you consider 4 set of variable x, 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 y, y, x, y, x, y, x, y, y, you can verify yourself. That's still one example. So x would flip 0 to 1, right? So if I do that, this flip to 1, 1, 1, and this flip to 0, 0, 0. Okay. And so it returned the cell with a plus sign. You can do that and use the y. So y is this matrix. So this means 0, 0 is 1, 0. So you apply this. And you see that this is 0, I. So 0 would turn it to I times 1. 1 would turn it to I, so minus I times 0. If you do that, so this only happened at the first and second bit. So using that rule, 0, 0 would turn into 1, 1, right? But you have 2i, so there's a minus. So 1, 1, and the third is x. It just flipped, but without changing the sign. Okay, and if you apply x and yx on the second component, it flipped to 0, but with a 2i here and 2 minus I multiplied to minus 1, so you get this. So meaning that you get a minus 1. Okay. And by permutation, you also have the other two cases. But now you can see that if I have a classical theory, and the most sensible assignment is that I should give some local value, like x1, x2, x3. They are not operator, they are just value. In order to explain this using classical theory, to explain this correlation, I have to assign a 3 variable, x1, x2, and then multiply to plus 1. I need to also have a y variable, right? y1, y2, y3, multiply to minus 1, etc. But now you multiply these 4 together, you get a contradiction because x1 appear twice, x2 appear twice, every variable appear twice. The left-hand side is 1, but the right-hand side is 1 times minus 1 times minus 1 times minus 1. You get a minus 1. Right? So there's a contradiction. And in fact, quantum mechanics, you can perform such measurement and verify these correlation. And then you can rule out a classical theory like this. Okay. So in some sense, this is a really strange or really sharp distinction of quantum mechanics from the classical theory. Okay. So maybe, yeah. Actually, I think I think this, I probably know how to explain this in a better way. So this is PR box. I think you should also sum over the outcome of B, because it doesn't matter what it should have, right? If you sum over all those, you actually assign that fixed A outcome probability does not change. Even if B is different. Okay. Yeah, so this is just, I just realized that this probably is a better answer than what I gave earlier. Right. So you're summing over the possible way of B, it should not matter. Okay. And this means that there's no way to do the signaling, right? I cannot just do some measurement and then the other side would see that occur. Okay. But PR box is beyond quantum mechanics. This GZ state violation is really at the heart of quantum mechanics. Okay. So we finished the first part. Any questions so far? No? Okay, so here things become more interesting because it's not just a philosophical debate of whether quantum mechanics is correct or not, or to verify that in experiment. But instead, you can turn quantum entangled state to something that are useful. The first thing that's probably the most famous one is the so-called quantum teleportation. So let me describe the scenario. So suppose you have a state, qubit state, and A and B is not known, so this is unknown state, and Alice has that state, and at the same time, Alice and Bob share an entangled state, so I denote 0, 0 plus 1, 1 here, but here I use indicate another one. So in fact, all these Bell states that we had before are useful. So the goal of Alice is to transfer this state, unknown state, to Bob, but to directly transfer the state maybe it's too expensive or too lossy. It's not practical to do that. And also, because the state is not known, Alice cannot infer what alpha and beta is. If she could just tell Bob what alpha, beta, and Bob could create that state. So with the shared entangled state, you can actually send this information to Bob by just telling Bob really limited classical communication. Okay, so meaning that you would in some sense destroy the state here and that Bob recreate the state there. Okay, so to describe that, I have to use mathematics. So we'll derive it with equations. The starting point is this. So the combined state of 1 and 2 and 3 is really just tensor product of these, right? So maybe you can ignore the coefficient, but that's try to see 1, 2, 3. If I reorient the state in terms of 1, 2, and 3, what I can do is that in this teleportation, you need to perform some kind of Bell measurement. Basically, it's in the Bell state basis, it's in entangled basis. And we know measurement will give us random outcomes. So we want to sort of list all possible scenarios. And in terms of 1, 2, and 3, maybe it will be outcome 1 and state become 1 and outcome 2 and state become a different form 2, etc. And so this is in the next page. So this really is just algebra. So what I'm doing is I'm going to unfold this into sum of 4 terms, right? I just redistribute everything. And what I'm going to do is rewrite, because I want the first 2 particles in the state of this basis, right? So in fact, what you can see is 0, 0 is phi plus phi minus up to coefficient. Okay, maybe this. And 1, 1 will be minus. And 0, 1 is psi plus psi minus. 1, 0 is psi plus minus psi minus. Okay, so what I'm going to do is replace this 0, 0 by this combination. I think I have that here. So I replace 0, 0 by this combination, 0, 1 by this combination, 1, 0 by this combination, which I derive here, 1, 1 by this combination, 1, 1. Okay, so let me erase this blocking that. Okay, if you feel the screen, the font is too small, you can use your view options and then make it bigger. You can make it bigger up to 300%. Okay, so I'm just rewriting. So far I'm rewriting, but in a way that I can associate with the measurement and the outcome. But you see that I have phi plus appear twice. So what I should do is I should combine them. I collect according the first 2 phi plus, you have A times 0 here. You also have B times 1. So that's why I have collect this. And you do it systematically. You consider if the first two state, 1, 2 particle is in phi minus, you have A0, and the other counts one here is B1 with a minus sign, and you do it, etc. So psi plus is associated with A1 plus B0, and psi minus is as additional sign. So you can actually relate this to the unknown state. So it's the same. So identical to unknown state, I just write as identity times the state. The second part differ by a minus sign, so it can be corrected, or this is the original state multiplied by a z. And this one just flip 0 to 1, so it's really just acting on the original state. This one is y times the original state up to I, okay? Because iy is this. They basically have a sign difference. So the upshot of this is using the three rules that we have seen. Actually, this we just use linearity and just recombining everything. This is really in really just superposition, depending how you arrange that. And now comes the measurement. This is the state that we have, right? The state. If we perform measurement on the first bit, the first qubit, you can get 4 possibilities. So measurement has 4 possible outcomes. For outcome 1, outcome 2, outcome 3, 4, right? And they appear with some probability, which actually is proportional to the norm square of the coefficient. You see that they're all 1/2. Each has probability 1/2 square. So they appear equally. Sorry. So, but if I obtain, let's say, phi plus, then I don't do, I need to do anything. So I just tell Bob, keep the state. That is what you get. If I measure, Alice measure and get phi minus, I know there's a z, additional z. So what Bob need to do is apply this z to cancel the z. So remember the x square equal to y square equal to z square equal to 1, right? So if it's the third outcome, this should be psi plus. Then you apply the x to the third particle to cancel out this x here, okay? And if the last outcome, you applied minus iy just to make it identity. So you can recover at particle 3, recover this exactly the same state that was unknown to Alice, and recover that at Bob's side. Okay, so this is the mathematical derivation of quantum teleportation, and it's really explained in this picture. So you have unknown state, you have shear entanglement, and you perform measurement 1 and 2. You need to tell Bob the rotation. It could be 0 or x, so 0 meaning identity, or x or y or z to act on your particle in order to obtain the identical one. Okay? Question? This is probably one of the most important protocol in quantum information. If you understand this one, you'll be able to understand a lot of subsequent protocol. Okay. This has been performed in experiment, and so that is something that is possible. Okay. I would have exercise for you that you would sort of extend this a little bit to more than 2 level, qubit, from qubit to qubit, and etc. There's another, I call now maybe slightly more advanced topic, but the derivation is quite simple, but also use the same rule that we have, the 3 rule. But I want to see if you have any question before I proceed.
Hello?
Yes?
Yeah. So if we have n qubits to teleport, how many conventional bits do we have to send?
Yeah, so if you have n bit to teleport, right, this will be the entangled state. You have n pair of, and there's n bit, n qubit state. Maybe this is n qubit. So each qubit, you need to have 2-bit information, right? It's either 0001, 1011, like you can just represent this. So each require 2 classical bit. So if you have an n bit total communication, classical communication is 2n bit. Okay. So let me see what we have next. Okay, so I'm trying to do something which is slightly simpler than teleportation. This is actually called gate teleportation. So let me explain what the goal is. You have an input state, also labeled as A0 plus B1. What you do is the second bit is in a plus state, and you entangle them by the so-called control Z gate. Yeah, so one of the reasons that I want to discuss this is I want to introduce a second entangle gate. This is control Z. Remember, we have control X. That will be this block being X gate, but here is Z gate. So it's even simpler. So it's 0, 0, 0, 1, 1, 0. Does not change. But 1, 1, you will have 1, 1, but have a minus sign. Okay. So what I would like to do is I want to perform measurement. So measurement. Okay. So I want to perform measurement in some basis. Measurement in this particular plus minus xi basis is explicitly written this. In terms of quantum mechanics, you can also write that as an observable, but you can verify these observable is such that they act on this equal to plus minus 1 times the basis. So this is the third rule, right? So rule of quantum mechanics. So observable define a basis also infer the observable and the value that you will get. So what is slightly different from the goal of teleportation here is I want to have the information teleport to here. So the input state should teleport to the second bit, but I also want to have some action. And you will see the action is related to a rotation. Let me just point out the central key component here. This is a rotation. If you remember, the Pauling matrices are related to rotation, generator of rotation. And S here is basically 0 or 1. So if it's 0, meaning that's nothing. So if it's 0, that's identity. If it's 1, the meaning that there is a Z. And this H here is Hadamard. Okay. So this is the goal. But I want to show that by using this simple circuit, what I can have is the information is teleport to the second qubit from the first qubit. And on top of that, there is a rotation. A rotation depending on the S measurement outcome labeled by S equal to 0 or 1. And this is the form of gate. So it becomes a rotation. Okay. So that's the goal. So next page is basically derivation, but I'm going to use the derivation just to reinforce what we have learned, really applying the rule of quantum mechanics. Okay, so this is the input. And plus state you can write as this, right? And after control Z, if A is 0, I will be ignoring this coefficient. If A is 0, the control is 0, you do nothing to the target, right? The target remains 0 plus 1. But when the control is 1, you apply the Z gate to the target. Z gate is flipping a minus sign to the 1 state. So this 1 state has a relative minus sign. Okay. Yeah, so we can actually simplify by saying that this A plus B1 times minus state. Okay, if you're not comfortable of saying two bracket back to back, you can put a tensor product notation. Okay, so I'm applying gate, right? This is rule 2. Right, rule 2 of quantum mechanics that I introduced. Then here I'm going to apply measurement. Right, so measurement it says it project to eigenstate of observable. So measurement, I'm only doing that on the first qubit. So eigenstates, right? Eigenstate can be plus or minus psi. So what I want to do is project, in the sense that I'm also inner product that vector into, let me call this psi 1, 2. Let me denote this by psi 1, 2. Okay, this is 1. To denote that I'm measuring only the qubit 1. So this is also one way to see the measurement. Okay, I'm really applying what we have learned, but I'm also filling the algebra. So remember that psi minus. Let me just rewrite. I think it's yeah, minus 1 xi over 2 0 2 plus. Okay, and if I do this, remember that this is a cat and this is bra. When you flip that, you also need to flip. You need to apply the complex conjugation. Okay, and apply this to A0 plus B1 minus. Okay, I label 1 because this is only applying to, there is a minus sign if the lower one comes in. So the minus sign, I just want to take both cases into account. So the calculation goes as follows. You can only take 0 dot into 0, right? Because 0 dot into 1 will be 1. 1 can only dot into 1. So there are only 2 contributions. So this means the first contribution is 0 dot into 0. I have a 0.0 is a number, so but the state that's left is the second bit, qubit, and the coefficient is a times psi over 2. The second term is from this one, 1 dot into 1, and there's a coefficient b. There's also coefficient from here, and then there's a minus, this minus. Okay, so this is almost, let me just write here. This is almost this is almost 0, right? But it's Hadamard acting on that. This is 1, Hadamard that. So, but there is also phase factor. Phase factor can be written as e to the I psi over 2 z, right? If it acts on a0 plus b1, then I can get the desired factor e to the I psi over 2 plus minus. But to get a minus sign, actually I have a minus sign to indicate the second case. And in order to turn the 0 to 1, I have Hadamard, so I just put Hadamard here. So this is the gate that I have. Hadamard e to the I psi over 2 z, and then z to the s. So s is -1, 0, or 1. 0, 1 is the outcome, so the plus minus, and this is a0 plus b1. Okay, so this is a slightly advanced topic, but I want to go through this and really do the detailed calculation to illustrate everything that you need to know. At least so far, you only need to apply the rule, right? Yeah, if you don't get exactly the detail, at least you know I'm not applying anything else more than what we already learned, right?
Is the position of z of s correct?
Yeah, it's correct. So, I mean, I can get the I want to get the phase first. I want to get the phase first, and then I correct the basis, right? If you ignore the basis, this is 0. This is like 1.
Okay.
Yeah, you can correct it, the basis later. Okay. If you have Hadamard first, then the z is not the z that apply. It would have to be x. Okay. But let me return to these. Basically, what I want to say is that this give rise to a rotation. Why is rotation useful? Rotation would allow us to achieve universal gate. So if I can get arbitrary rotation, then I can get a quantum circuit. Any quantum algorithm, as long as I can write in quantum circuit, I can decompose into 1 and 2 qubit gate. But we'll come back to that gate later. Okay. So I have, if this is an advanced topic, so you can ignore this the first time of seeing this. But a related one to the teleportation is the so-called entanglement swapping. But this is easy to just draw by the diagram. If you have entangled state as indicated here, a source to Charlie, Bob, and Bob maybe have another one, or so maybe B1, B2, entangle with Alice, right? If I perform the measurement here and then relay the information to Bob, I'm teleport B1 to C, right? In some sense, whatever B1 has would appear here at the C location. But B1 was previously entangled with A. So that means at the end of this Bell measurement and also classical information, I actually establish entanglement between A and C. Okay. Does that make sense? I'm using teleportation to explain that. Teleport, you can just think of the B, the unknown state would be copied to the C here. Okay. And whatever you have here would disappear, would be destroyed. So that means you would have A and C in the entangled state. Okay. So this is useful because if you have many stations, you have any station like A, B, C, D, etc. up to Y and Z, and you don't have a long distance entanglement, but you can create from a series of entanglement swapping. So you do the swapping between A and D. So by doing this, you get AD. By doing that, you get WZ, etc. And then by doing a further entanglement swapping, you get really long distance entanglement. So A and Z become entangled even if they were not before, right? So in fact, this can be used to do quantum communication. So quantum communication. And you might have known that Professor Figueroa has a lab that can implement this. And his goal is to set up a large quantum internet using entangled states. Okay. Yeah, this one that maybe I erased. So yeah, so entanglement swapping is the basic protocol to establish long-range entanglement. So that could be used to form a quantum internet. Yeah. Okay, so this I say would also be a slightly advanced topic, but the idea is simple. So let me just tell you what it is. It's actually similar to all what we have discussed, but let's look at using a single state. The single state is really special. You're going to see that in your second homework. In fact, because it's anti-symmetric, right? If you swap these, you get a minus sign. So for such anti-symmetric state, you can decompose this in terms of any one Cupid state, its orthogonal state, minus its orthogonal state, and the state itself, up to some phase factor. So this entangled state, like the singlet, is interesting because if I perform measurement in psi and psi perpendicular basis, if I can perform that, sometimes I get psi, sometimes I get psi perpendicular. If I get psi, I know the other side get psi perpendicular, right? If I get, so A gets psi and B gets psi perpendicular. If A gets psi perpendicular, B would get psi. So in some sense, by A performing the experiment, I can project B state to either psi or psi perpendicular. This is called remote state preparation, meaning that Alice is preparing the state for Bob. But this, in general, cannot succeed with 100% probability because if I get psi on either side, Bob is in the perpendicular state. But how do I rotate this to the desired side that I want? In general, this is not possible. This is it only for special state, the so-called equatorial state. So that's one of interesting application. So let me pause here to see if you have a question, because we're close to the end. We'll come back next week and continue on the super dense coding. Any questions? Maybe if not, could we do a simple poll here about today's class? I want to gauge how everybody's doing. For those who are still here, can you reflect what's going on here? Is it too fast, too slow? I know topics get challenging, but that's the case for new subject. Okay. Yeah, if you have to leave to another class, please go ahead. Let's take 10 more seconds and I will share the poll results. Okay. I'll share the results. I'll try to copy this. Okay. Yeah, so thanks for the feedback. So yeah, we will end the lecture here. You can leave. I think next Monday is a holiday, right? We don't have a class.
Yeah.
Can interview confirm?
That's correct.
Okay, so we'll see you on Thursday. And I'm pasting the results of the poll so it can be recorded into the video. Okay, I'll see you next time.
See you.
See you.
Bye-bye.
And don't
See you.
forget the homework.
Okay.